Hi there, I'm from Grade 8 and today I'm going to present our chemical reaction project report. The chemical we need to produce is ethylene, and in this team consists of 4 members, which is Hafika, Muhammad Ashraf, Nur Muhammad Aiman, and me, Daishan.
Ethylene, also known as ethene, is a hydrocarbon with a chemical formula C2H4. This is a colorless, flammable gas with a sweet and floral odor. This is naturally produced by plants as part of their growth and development, and also artificially produced by chemical industry for use in various applications. It is used as raw material for manufacturing a variety of compounds, including polymer, solvent, and resins. It is also used in the production of goods such as detergent, rubber, and textile. In agriculture, it also used as a growth regulator for crops and plants. Additionally, it is used as an aesthetic in medicines overall. It plays an important role in the chemical, agriculture, and medical sector for the global economy. There is 2 objectives in our study. First, we need to choose the appropriate method and route for synthesizing 100 kg per day of ethylene. And the second is we need to construct a reactor to produce the 100 kg per day of ethylene.
Now, we move on to the background of ethylene. Ethylene is the simplest organic compound which is in colorless form, flammable, and have a sweet taste and odor. Ethylene was synthesized by a collaboration of 4 Dutch chemists in 1795. Typically, ethylene is made from ethanol and also sulfuric acid. As the time passed by, George Oliver Kerm Jr. provided a vision for ethylene process as it has more advantage compared to the others. Kerm and the team developed a technique known as thermal cracking to produce ethylene from ethane.
For the application of ethylene, ethylene is a simple organic molecule present in the form of gas. The main functions of ethylene are fruit ripening, leaf abscission, suppress stem, root elongation, and stimulate flower. Furthermore, ethylene suppresses lateral bud formation and helps to stimulate latex flow in the rubber tree. Polyethylene, for instance, is the most widely used plastic in the world and is used in a wide range of products such as packaging, toys, and household items. Ethylene oxide is used to produce ethylene glycol, which is a key ingredient in the production of antifreeze and coolant fluids. In overall, ethylene plays an important role in a wide range of industries, particularly the chemical, agricultural, and medical sectors of the global economy. Its versatility and low cost make it an essential ingredient in the production of many different products, from plastic to textiles to chemical and medical equipment.
Throughout our literature review, we have obtained the physical property of ethylene. The physical properties of ethylene were obtained from the NIST website, PubChem website, and Engineering Toolbox website. The data was tabulated and shown at beside. There are 3 processes to produce ethylene. The first is steam cracking, and the second is partial oxidation of hydrocarbon, and the third is pyrolysis cracking. Ethylene is made via steam cracking. High heat and pressure split bigger hydrocarbon molecule into smaller ones. A feedstock such as natural gas, naphtha, is chosen first. The clean feedstock is evaporated in the furnace at a high temperature and rapid mix with the steam. Let's proceed to the partial oxidation of hydrocarbon. Partial oxidation is a technique used to create ethylene and other effluent from hydrocarbon. It involves the partial oxidation of the hydrocarbon feedstock with the use of oxygen and a catalyst. The process starts with the selection of the feedstock, which can be any several hydrocarbons, such as propane and butane. The feedstock is then combined with oxygen and a catalyst such as copper and silver, before being heated to the required reaction temperature. Now, let us proceed to the pyrolysis cracking. Pyrolysis cracking is a method for producing a variety of products by decomposing organic material such as biomass at a high temperature and pressure. Biomass such as wood, agricultural leftover, and garbage may be pyrolyzed to create ethylene and other effluent. The generation of ethylene by pyrolysis is often less efficient and more costly than alternative process such as steam cracking or partial oxidation, and is therefore not extensively used in commercial production. However, it has benefit of using sustainable feedstock such as wood and agricultural leftover, which are products from the plant matter rather than the fossil fuel.
For the synthesis route, we have 2 routes, which is steam cracking of ethane and partial oxidation of methane, and then we will proceed to the selection and justification. The first synthesis route is the steam cracking of ethane. Steam cracking is commonly performed on ethane, naphtha, and other hydrocarbon feedstock. A plug flow reactor, which is known as PFR, passes through the firebox of furnace during the steam cracking process. The most commonly used feedstock, ethane, requires the highest temperature of 800 degrees to 900 degrees Celsius to crack, which means it consumes enormous amounts of energy to do so. Steam cracking performance is affected by the reactor pressure, steam hydrocarbon ratio, and temperature in addition to temperature. So, the diagram shows the reaction mechanism, which is initiation, propagation, and termination, and the other diagram is the schematic of ethane steam cracking furnace. The second synthesis route is the partial oxidation of methane. Partial oxidation is the process used to produce ethylene and other olefins from hydrocarbons using oxygen and a catalyst. The first step in the partial oxidation process is choosing a feedstock, which is methane. Ethylene-ethane ratio increases with the reaction temperature. For temperatures above 750 degrees Celsius, although the conversion of methane remains constant, the increase in ethylene and ethane ratio is ascribed to enhance the in-rate ethane dehydrogenation. So the diagram shows the graph of influence of CH4O2 ratio fed to the reactor over methane conversion. and the other diagram is the schematic of partial oxidation of methane. So, for the selection and justification, we can conclude that the process of production of ethylene through partial oxidation of methane was chosen to be discussed in this project. Partial oxidation of methane is a process that involves the controlled oxidation of methane to produce a variety of chemicals and materials. Methane is readily available and inexpensive feedstock, making the partial oxidation process cost-effective. The process is also high efficient with a high yield of ethylene. In addition, the process can be easily scaled up to meet the increasing demand for ethylene. The partial oxidation process produces a low volume of byproduct gases, making it environmentally friendly. In overall, partial oxidation of methane is an attractive method for producing ethylene due to its cost-effectiveness, efficiency, scalability, and environmental friendliness. It is an important contributor to the chemical industry and supports the achievement of the SDG.
Throughout our study on the academic paper, we have found out the rate constant expression for the trade reaction. The K value is varying within the range of 200 to 2000 Kelvin. And we have listed down the expression in the table, and the reference was stated in below.
Okay, for the next, I will explain about the reactor system. The reaction is continuous because the catalyst is used in the production reaction, and the reactor is designed for a large production for 100 kg per day. A packed reactor PBR has a higher conversion rate than other reactor because the catalytic weight is greater. PBR have a low operational cost compared with base reactor, and high temperature and pressure are also effective using this product. Okay, for the stoichiometric table, the overall reaction is 2CH4 plus 2 will produce C2H4 and H2O. The assumption for the reaction is the process is based on steady state operation. Heat loss to the surrounding is negligible. Kinetic energy and potential energy throughout the entire process are negligible, and the process is in isothermal and isobaric condition. Okay, I will continue for the stoichiometric table. Since the reaction is gas phase, thus the volume is changed. In this case, the condition is isothermal and isobaric, so there is no change in the temperature and pressure. From the stoichiometric table, we can insert formula, and then we get the remaining and concentration. For the total remaining, Ft equal to Ft naught plus delta Fa naught at. For the concentration, Ct equal to Ct naught plus delta Ca naught at.
For multiple reaction part, we have 4 reactions and we assume all reactions are elementary. The first reaction we have is initiation reaction. We have methane react with oxide and produce methanite and also hydroxide. The second one is propagation reaction. We have methane react with oxygen, produce methanite and also hyperoxy radical. The third one is termination reaction. We have methanite react with methanite itself and it produces ethylene and hydrogen. From all the 3 reactions above, we get for the overall reaction, which is methane react with oxygen to produce ethylene and also water. Next, we calculate the value of rate constant K for all reactions based on the rate law expression in reaction kinetic. The value of temperature T is 973 Kelvin. The value of K1 we get 6.5502 times 10 to the power of negative 13 cm3 per mole per second. The value of K2 we get 1.2785 times 10 to the power of negative 32 cm3 per mole second. K3 we have 4.2069 times 10 to the power of negative 16 cm3 per mole per second. And K4 we have 75.63 cm3 per mole per second. Then, we calculate the value of activation energy based on the Arrhenius equation. For the reaction 1, we get 409.10 kJ per mole. Reaction 2, 589.97 kJ per mole. Reaction 3, 282.29 kJ per mole. And for the last reaction, overall reaction, we get 147.15 kJ per mole. After that, we determine the relative rate for each reaction, and also we determine the net rate law for each compound in the reaction. Now, we look into the algorithm part. We have 2 conditions here, which is isothermal and isobaric and also non-isobaric. For the isothermal and isobaric condition, we assume isobaric condition, which is P over P naught equals to 1. Isothermal condition, which is T over T naught equals to 1, and also the side reaction is neglected. We have basis here, which is 0.4951 mole per second ethylene produced. And based on the reactor that we use, which is PBR, we have the design equation ds over dw equals to negative Fa over Fa naught. And we have the rate law and also the stoichiometry that we can get from the stoichiometric table. For the second condition, we have non-isobaric condition. We assume gas phase in reaction. Initial concentration and also volume remain constant. The side reaction is neglected, and we assume the value of the final pressure, which is P, equals to 5 atm. And same here, we have the design equation for the PBR, the rate law and the stoichiometry that we can get from the stoichiometric table.
For the calculation part, we use the Polymath software. So the first part is the isothermal and isobaric. First of all, we just state the chemical reaction equation, which is 2A plus B equal to C plus 2D. Then we state the PBR design equation, which is dW over dx equal to Fa naught divided by negative Ra. And we state the X naught, XF, which is the final conversion of 0.632 and the W naught. Then we continue with the rate law, which is Ra equal to negative K, Ca square Cb. And the rate law we can get from the chemical reaction equation. Then we just state the equation for calculation, such as initial concentration of species A, design parameter and the stoichiometry. And finally we get the W, which is the weight of catalyst. we get 0.5946 kg. For the non-isobaric, the coding is quite similar with the first part. The only difference is we assign the final pressure. So the initial pressure is 6 atm and we assign the final pressure is 5 atm. So the stoichiometric equation for CA, CB, CC and CD, all of them will multiply by Y. The Y is the pressure drop, which is P over P naught. And finally we get the W, the weight of catalyst, of 1.0274 kg.
So, for the conclusion is, we decided to choose the partial oxidation of ethane is the most economical way to produce ethylene. Next, the reactor that we choose is the back-bed reactor, which is PBR. The operation condition is T equal to 700 degrees Celsius on also the pressure is in 6 atm. The catalyst that we use is magnesium oxide. To produce 100 kg per day of ethylene, 0.5946 kg of catalyst needed for isothermal and also isobaric condition. For non-isobaric condition, we need 1.0274 kg of catalyst.